November 25, 1940, 15,000 feet over occupied France. Flight Sergeant David Collins sat at the engineer's station of Manchester bomber L-7320, monitoring gauge needles that had been steady for 2 hours. The twin Rolls-Royce Vulture engines hummed through the airframe. Port side oil pressure, 85 pounds per square inch. Temperature, 90 degrees Celsius. Normal. Collins logged the readings. Outside, darkness stretched in every direction. Stars above, blackness below. The crew relied on instruments and dead reckoning to find their way home. The vibration started small, a tremor through the engineer's panel. Collins felt it before he saw the gauges move. Port engine oil pressure dropping, 80 pounds, 70. Temperature climbing, 95 degrees, 100. He keyed the intercom. Skipper, port engine running hot, oil pressure falling. Pilot acknowledged, reduced power to the port Vulture. The vibration grew worse. Collins watched the temperature needle swing past 110 degrees. Orange glow appeared outside the port nacelle window. Fire. He hit the engine fire extinguisher. Nothing happened. The flames spread along the cowling. Pilot feathered the propeller, cut fuel to the port engine. Too late. The asymmetric thrust from the starboard engine alone pulled the Manchester into a banking turn. Collins grabbed for the escape hatch. The port wing buckled. Metal screamed. L-7320 dropped nose first into the darkness. All 7 crew died on impact. The 9th Manchester lost to engine failure that year, not to German fighters, not to flak. To its own. By spring 1941, the Royal Air Force was losing Manchester bombers faster than factories could replace them. 79 aircraft destroyed by mechanical failure out of 200 produced. Pilots called it a death trap. The Air Ministry gave Chief Designer Roy an ultimatum: fix the Manchester in 3 months, or the entire program would be cancelled. The Vulture engine was supposed to be Rolls-Royce's Triumph. 2 Peregrine V12 engines joined at a common crankcase, 1,760 horsepower from each. Enough thrust to carry a heavy bomber deep into Germany and back. On paper, the design was elegant. In practice, it was a death sentence. The coupling created harmonic vibrations that cracked cylinder blocks. Connecting rods failed under stress. Oil seals leaked at the junction point. Cooling systems couldn't handle the heat generated by 24 cylinders sharing one crankcase. The Vulture ran hot, leaked oil, and caught fire with regularity that terrified crews. December 1940, Manchester serial R5768 crashed on takeoff from RAF, starboard engine failure, 4 dead. January 1941, Manchester L-7281 lost both engines over the North Sea. Entire crew drowned. February 1941, Manchester L-7300 caught fire during landing approach. Engine explosion killed the pilot and navigator. By March 1941, squadron commanders refused to send Manchesters on operations without written orders. The mathematics were brutal. 200 aircraft produced. 79 lost to mechanical failure. 0 lost to enemy action that couldn't be attributed to the aircraft's inability to escape after engine problems. Survival rate, worse than flying obsolete biplanes. The Air Ministry scheduled an emergency meeting for April 15, 1941, at its facility. Attendees included Roy's chief designer, his chief engineer Stuart Davies, and 3 Air Ministry officials who had authority to cancel the entire Manchester program. The ministry's position was clear. Britain needed a heavy bomber immediately. Germany was bombing British cities every night. RAF Bomber Command had no aircraft capable of striking back with equivalent force. The Manchester was supposed to fill that role. Instead, it was killing RAF crews faster than German fighters could. Had 3 months. Fix the fundamental problem, or the Air Ministry would cancel production and divert resources to expanding Wellington and Stirling production. No extensions, no second chances. The obvious solutions had already failed. Rolls-Royce couldn't fix the Vulture. The company had been trying since 1939. The coupling design was fundamentally flawed. Decoupling the engines meant starting over with a completely new. Britain didn't have time for that. Finding a more powerful engine wasn't possible. The Bristol Centaurus wasn't ready for production. The Sabre had worse reliability problems than the Vulture. American engines like the Wright Cyclone weren't available in sufficient numbers. Every alternative would take years to certify, integrate, and manufacture. Reducing the Manchester's weight wouldn't help enough. The aircraft already carried minimal armor. Removing defensive guns would make it helpless against German fighters. The fuel capacity couldn't be reduced without eliminating range to reach targets in Germany. Proposed something else. Something that violated conventional bomber design. He wouldn't give details at the April meeting, only equations. Stuart Davies, his chief engineer, did the calculations during the presentation. The Air Ministry officials watched Davies write numbers on a blackboard. Power output increased by 46%. Weight distribution balanced across greater wingspan. Reliability proven in operational combat. One official interrupted. "You're talking about a complete redesign. We don't have time." Response: "We don't have a choice. What we're doing now is killing pilots." The Air Ministry approved the proposal on May 2, 1941. Prototype construction would begin immediately. First test flight, January 9, 1942. 8 months to prove a concept that no other aircraft manufacturer had attempted. If the test flight failed, Britain would enter 1942 without a heavy bomber capable of reaching Berlin. Left the meeting with authorization to proceed. He also left with a question nobody had answered. If this failed, what would the RAF use to strike Germany? Solution violated every principle of heavy bomber design. Instead of fixing the Vulture or finding a more powerful replacement, he proposed removing both engines entirely. He would install 4 Rolls-Royce Merlins. Fighter engines on a heavy bomber. The Merlin produced 1,280 horsepower, 480 horsepower less than a Vulture. Putting fighter engines on a heavy bomber seemed insane. Stuart Davies had done the mathematics. 2 Vultures generated 3,520 total horsepower. 4 Merlins generated 5,120 horsepower. More power, yes, but 4 engines meant 4 times the engine mounts, 4 cooling systems, 4 sets of controls, 4 propellers. The additional weight and drag would consume most of the power advantage. And Merlins were designed for different work. High-altitude sprint performance in Spitfires, short bursts of maximum power, not sustained cruise power hauling bomb loads for 7 hours. The thermal management seemed impossible. Understood the mathematics looked wrong, but he saw something the calculations missed. The Manchester's 2 Vultures sat close together near the fuselage. When one failed, asymmetric thrust made the aircraft uncontrollable. Flight Sergeant Collins died because the port engine quit and the starboard engine alone pulled the Manchester into a fatal turn. 4 Merlins spread across a 102-foot wingspan would balance thrust, even if 2 engines failed. 1 engine out, the opposite outboard engine compensated. 2 engines out on the same side. The 2 engines on the other side still provided balanced thrust across the wing. The aircraft remained controllable. Crews could fly home. And Merlins had one advantage Vultures never achieved. They worked. Spitfire squadrons flew Merlins through sustained combat, hundreds of Spitfires operating daily. The engine was proven, reliable, and already in mass production. No development time needed, no certification process, just installation. The precedent existed. Boeing's B-17 Flying Fortress used 4 engines, but those were Wright Cyclone radials, specifically designed for bombers. Large, air-cooled engines built for endurance. Nobody had ever put liquid-cooled fighter engines on a heavy bomber. The technical challenges were substantial. 4 independent engines created vibration that would tear the airframe apart. The solution was synchronization. 4 engines working independently became 4 competing forces. 4 engines synchronized to within 50 revolutions per minute became one system. The propellers would turn in precise coordination. Power pulses would align. The airframe would experience smooth, distributed thrust instead of destructive oscillation. 50 RPM was the threshold. Beyond that difference, standing waves built up in the metal structure. Vibration accumulated. Fatigue cracks appeared. Within 50 RPM, the 4 engines functioned as a single. calculated that propeller governors could maintain that tolerance. Each engine would drive its propeller through a reduction gearbox. The governors would hold constant speed regardless of throttle changes. Set all four to 2,400 RPM, and they'd stay within 50 RPM of each other. The wing required complete redesign. The Manchester's wing measured 90 feet across. Extended it to 102 feet. The additional 12 feet weren't just for engine spacing. More wingspan meant more surface area to generate lift, better weight distribution for the outboard engines, lower wing loading per square foot. Wing loading determined how much weight each square foot of wing had to support. The Manchester carried 63 pounds per square foot at full weight. The Boeing B-17, considered one of the best heavy bomber designs, carried 38 pounds per square foot. Its new design would carry 67 pounds per square foot, higher than the Manchester despite the larger wing, because maximum takeoff weight increased to 72,000 pounds. Higher wing loading should have created a dangerous aircraft. High wing loading meant high stall speeds, less margin for error, but compensated with airfoil shape. The wing profile generated maximum lift at the specific speeds and angles a loaded bomber operated. The Manchester's wing was designed for two powerful engines providing brute force. The new wing was designed for four synchronized engines providing distributed thrust. The cooling system solved the thermal problem everyone considered impossible. Spitfire pilots pushed Merlins to maximum power for minutes. Bomber operations required cruise power for hours. Different thermal loads, different requirements. Mounted radiators in housings under each wing between the fuselage and inner engines. Air flowing under the wing at cruise speed provided continuous cooling. The system included intercoolers to reduce intake air temperature and separate oil coolers for each engine. Every engine ran independently, but within tolerances that kept all four at matching temperatures. If one engine started running hot, the pilot could adjust mixture and throttle, while the other three maintained cruise power. If an engine had to be shut down completely, the cooling system for that engine simply stopped working. The other three continued normally. No cascading failures, no thermal overload. The design was complete by July 1941. Prototype construction began immediately. The first airframe took shape in its factory through the autumn. By December, the aircraft existed. 4 Rolls-Royce Merlin XX engines mounted on wings that looked disproportionately long for the fuselage. Everything calculated on paper now existed in metal and wood. January 9, 1942. The test flight would prove whether 4 weak engines could outperform 2 strong ones. January 9, 1942. Aerodrome Cheshire. The prototype sat on wet tarmac under gray winter sky. Registration BT-308. 4 Rolls-Royce Merlin XX engines mounted on wings that extended 51 feet from the fuselage centerline on each side. Chief Test Pilot Sam Brown completed his pre-flight walk-around. He'd flown the Manchester. He knew what happened when engines failed. This aircraft had 4 engines, 4 points of potential failure, but also 4 sources of thrust if synchronization theory worked. Brown climbed into the cockpit, started engines 1 through 4 in sequence. All 4 Merlins spooled up. He checked the propeller governors, set all 4 tachometers to 2,400 RPM. The needles settled within 30 RPM of each other, within tolerance. He advanced throttles. BT-308 accelerated down the runway. Rotation speed, 105 miles per hour. The aircraft lifted at 110. Smooth. No vibration through the control column. No asymmetric pull from unbalanced thrust. Brown climbed to 8,000 feet and leveled off. The real test began. He throttled back engine number 2 to idle. The aircraft remained stable. Slight yaw to port, easily corrected with rudder trim. He throttled back engine number 3. 2 engines producing 0 thrust. The Manchester would have been in a death spiral. BT-308 held altitude and responded normally to control inputs. Brown pushed the test further. Engines 2 and 3 still at idle. He reduced power on engine 1 to 50%. 3/4 of the aircraft's thrust now came from the single starboard outboard engine. BT-308 required constant rudder pressure but remained controllable. A pilot could fly this aircraft home with 3 engines damaged. He restored power to all 4 engines and began descent. Landing speed, 95 miles per hour. Touchdown smooth. After 2 hours and 17 minutes, Brown shut down the engines and filled out his test report. 2 words summarize the flight: no vices. The aircraft had no handling quirks, no dangerous tendencies, no surprises. It flew like a stable, predictable heavy bomber despite using fighter engines. The Air Ministry placed an order for 3,000 aircraft in February 1942. The name Lancaster replaced Manchester on production orders. By March, the first production Lancasters rolled out of factory. By April, No. 44 Squadron received operational aircraft. By May 1942, Lancasters were bombing Germany. German intelligence officers started finding Rolls-Royce Merlin data plates in the wreckage. The same engine they'd seen in downed Spitfires. Same serial number patterns. Same specifications. Now appearing in heavy bombers that shouldn't have been able to fly. Initial reports from Luftwaffe fighter pilots described the Lancaster as slightly faster than the Manchester, but otherwise unremarkable. That assessment changed in July 1942 when Lancasters began operating at altitudes German fighters struggled to reach, 22,000 feet with full bomb loads. The Merlin's supercharger characteristics gave the Lancaster performance at high altitude that the Manchester never achieved. By August 1942, RAF Bomber Command operated 8 Lancaster squadrons. By December, 20 squadrons. The production rate exceeded losses. For the first time since 1939, Bomber Command had a heavy bomber that could reach any target in Germany and return with acceptable loss rates. The Lancaster carried 14,000 pounds of bombs in a standard configuration, compared to the Manchester's maximum of 10,350 pounds, compared to the B-17's typical load of 4,000 pounds. The Lancaster's bomb bay measured 33 feet long, unobstructed by internal structures, a straight tube from nose to tail that could accommodate weapons the Americans couldn't carry. In 1944, Barnes faced a problem that required physics most engineers considered impossible. Had designed the bouncing bomb that breached the Mona and Ader dams in May 1943. Now he wanted something that didn't bounce, an earthquake bomb, 22,000 pounds of high explosive in a single streamlined casing. The problem wasn't building the bomb, it was finding an aircraft to carry it. The Lancaster's maximum bomb load was 14,000 pounds. Grand Slam weighed 22,000. Even if it physically fit in the bomb bay, the structural limits couldn't handle the weight. Wings would fail. Landing gear would collapse. Engineers modified 23 Lancaster BI airframes into special variants. They removed the nose turret, eliminated the mid-upper turret, stripped armor plating, cut open the bomb bay doors, and reinforced the surrounding structure. The modifications reduced empty weight by 3,500 pounds and created clearance for the massive weapon. Even with weight savings, a Lancaster special carrying Grand Slam operated at 72,000 pounds gross weight, 4,000 pounds over the original design limit. The aircraft would be flying at the absolute edge of structural capability. March 14, 1945. Squadron leader Charles lifted off from RAF Spa in Lancaster PD-119. Grand Slam hung in the modified bomb bay, its nose protruding slightly forward of the bomb doors. Target: Bielefeld Railway Viaduct in Germany. The viaduct carried the main rail line supplying German forces in the Ruhr Valley. Previous raids with conventional bombs had damaged, but not destroyed it. Climbed to 18,000 feet. 4 Merlin engines pulled the overloaded Lancaster higher than most bombers operated. The synchronization held, all 4 engines running within 40 RPM of each other despite the extreme weight. At 14:30 hours, the bomb aimer released Grand Slam. 22,000 pounds fell for 41 seconds before impact. The viaduct didn't just collapse. Over 100 yards of structure dropped into the valley. The rail line was severed completely. German repair crews estimated 6 months to rebuild. When returned to Spa, ground crew inspected PD-119. The wing main spars showed visible deformation, metal stressed beyond normal operating limits. The aircraft had flown at the absolute edge of structural failure, but 4 Rolls-Royce Merlins had lifted it. The same engines that powered Spitfires to intercept German fighters at 25,000 feet had just hauled a 36-ton bomber with an 11-ton bomb to target and returned. German intelligence analysts received reports of the super bomb. They recalculated the numbers. The mathematics still showed it was impossible. One engine type could not perform across that range of applications. Fighter engines provided high power for short duration. Bomber engines provided moderate power for long duration. An engine optimized for one role couldn't work in the other. German aviation doctrine operated on specialization. The Junkers 211 powered medium bombers like the 111 and Junkers 88. The BMW 801 went into the FW 190 fighter. BMW radials powered the FW 200 Condor maritime patrol aircraft. No crossover, no adaptation, each designed for a specific mission profile. The HE 177 demonstrated what happened when Germany tried to break that rule. The Air Ministry wanted a heavy bomber with range to reach Britain and speed to evade fighters. HE's solution used 2 engines, but each engine was actually 2 Daimler-Benz 605 inverted V12 engines coupled together. The DB606 produced 2,700 horsepower, powerful enough for a heavy bomber. The coupled design saved weight and reduced drag compared to 4 separate engines. On paper, it solved everything. In operation, the DB606 caught fire constantly. The coupled crankshafts created harmonic vibrations that cracked engine blocks. Cooling systems failed. By 1944, the He 177 program was effectively canceled after losing dozens of aircraft to engine fires. Germany never fielded a successful 4-engine heavy bomber. Britain took the opposite approach. The Merlin wasn't designed for one mission. Rolls-Royce produced Merlins for Spitfires, Hurricanes, Mosquitoes, Lancasters, and the American P-51 Mustang. The same basic engine architecture scaled across every role. Different supercharger configurations for different altitudes. Different reduction gearing for different propeller speeds, but the core design remained constant, reliable, proven. When needed 4 engines for the Lancaster, he didn't wait for a specialized bomber engine to be developed. He used what already worked. By May 1945, Lancaster bombers had flown 156,000 sorties over Germany. They dropped 608,000 tons of bombs. 7,377 aircraft built across 3 years of production. The loss rate averaged 2.8% per sortie, lower than any other British heavy bomber. Crews preferred flying Lancasters over any other aircraft in bomber command. The same Rolls-Royce Merlin that pushed 3-ton Spitfires to 600 kilometers per hour had lifted 30-ton Lancasters, carrying 10-ton Grand Slam bombs across Germany every night for 3 years. German engineers had called it physically impossible because they calculated the power requirements of one engine operating in one role. They missed the system of 4 engines providing distributed, balanced thrust. The difference wasn't just engineering, it was doctrine. German aviation development focused on optimization. Create the perfect engine for each specific role. Maximum efficiency within narrow parameters. The approach worked when missions matched predictions. It failed when reality demanded adaptation. The He 177 caught fire because coupled engines couldn't handle vibration. The 211 couldn't power aircraft outside its design envelope. German bombers couldn't carry the weapons British bombers dropped routinely. British aviation development focused on adaptability. Create a reliable engine that could be modified for different roles. Accept slightly reduced efficiency in exchange for operational flexibility. The Merlin never achieved the absolute peak performance of specialized German engines in any single category. But it worked across every category. Fighters, bombers, reconnaissance aircraft, maritime patrol. The same engine architecture served them all. Roy's insight wasn't discovering that 4 engines provided more power than 2. Stuart Davies had calculated that in the first meeting. Understood that 4 reliable engines providing balanced thrust across a wider wingspan created a system that survived damage, maintained control, and operated at the edge of structural limits without catastrophic failure. Flight Sergeant Collins died because the Manchester's 2 Vultures created a single point of failure. When the port engine quit, asymmetric thrust from the starboard engine alone killed the aircraft. Lancaster crews flew home with 2 engines shut down because the remaining 2 engines provided balanced thrust. The system survived what would have destroyed the Manchester. The Lancaster served in RAF squadrons until 1963. Some variants continued in Canadian and French service into the 1960s. Modern multi-engine aircraft design still uses the principles implemented: distributed thrust, redundant systems, engines proven in other applications rather than purpose-built for one role. German engineers examining Lancaster wreckage in 1945 wrote reports stating the aircraft was physically impossible. The mathematics showed one engine type couldn't serve across such different roles. But the Lancaster had been bombing Germany for 3 years, using exactly that engine. Sometimes impossible is just something you didn't think through completely, and your enemy did. The history of World War II aviation is filled with moments where conventional thinking lost to unconventional engineering. If this story changed how you see the impossible, leave a comment about which wartime technology you want explored next. And if you haven't subscribed yet, hit that button. There are more stories like this one waiting.